Hey guys,
What up?
how's it going?
Going all right.
Cool.
How's it going for you?
Good. Yeah, I have a little bit of a setup in my office now. Like on Tuesday, I was just using my laptop, but now I actually have like my webcam set up on my desktop computer. So this is a lot nicer.
You had to imagine using a laptop for everything isn't ideal.
Yeah.
Professor, how does it feel being back on campus?
Oh, it's good. I'm definitely much more productive on campus than I am at home. I think it's just, in my home, all I want to do is just relax. And so I think working from home was fun at first, but then, I really started to feel the burnout at the end of last semester. So I think just having that separation again between my work and my home has been really nice.
Oh, Professor, I have a quick question.
Mhm.
Is revenue and benefits kind of like the same thing?
So revenue is a kind of benefits. And so benefit is just any kind of cash that's incoming, that's coming into you. And so, another example of a benefit that's not a revenue is like a salvage value, right? And so if you sell your property, you sell an asset, then you get a benefit, but that's not necessarily revenue. So revenue usually refers to like regular income that you get from selling your product.
Oh, okay. Okay, thank you.
Mhm.
Hey, Professor. I was wondering if I could ask you a quick question.
Sure. What's up?
All right. So I was doing the homework last night, and I got pretty much all the way till the end, but I realized I don't know for sure yet, but I don't think we can do the last problem, part C and D yet, just because I don't think we've gone over anything about like gradient or something like that.
Right. Yes. So we're going to go over gradient today. So after today, you should be able to do the very last couple.
Okay, for sure. I just wanted to make sure it's not just me.
Oh yeah. We haven't covered it yet, and so we've done three so far, but yeah, the last two you need today's lecture to do that.
Okay, sounds good. Thank you.
Yep. Yeah, Samson, you should be able to do everything on the 441 work. Yeah.
Professor,
Yep.
I have a crazy question.
Sure.
Do like professors get, I know that like professors get like parking permits at a discount, but does the standard price also go up for you guys too?
Yes.
Oh, wow. Okay, I didn't know that.
Mhm. Yeah, it's been a thing, or the union is kind of upset about that too. I mean, as is all the students as well. So, yeah.
Yeah, I didn't think it was gonna affect you guys. I didn't know that, of course.
Mhm. Yeah, it was. There's a lot of friction with the administration just because last year they reported so much like budget surplus, and we also got the huge gift from what's her face, the wife of Amazon, Mackenzie Scott. She donated $40 million to the school, but then they're they're raising fees on stuff like that, and they're not paying the staff anymore too. So it's been an ongoing battle with the administration. Okay, it's 1 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
So far, so good.
Good,
Afternoon, Professor.
good, good. Good afternoon to you too.
Pretty good. How about you?
I'm good. I'm good. Thanks for asking. Yeah, this is so you probably noticed from Tuesday, my setup is a little bit different. So I actually finally installed my webcam in my office. I have 2 brand new monitors here, and so I can see my notes on like a big screen now. So it's not just on my little laptop screen. So this is really nice. So I'm still enjoying that right now. Yeah. Okay. All right, so today we're going to hopefully finish up our notes on lecture note 01 on the time value of money. Okay, and so last time what we went over was this whole concept of equivalence, and so we'll finish up basically talking about that, and we'll kind of round out our discussion of that. And after today, you should have everything you need to finish up the homework. And so I was talking to someone before the lecture, and so up to this point, you should be able to do basically everything on the homework that's available except for the last 2 parts of the last question. Okay, but after today you should be able to have everything that. Okay, and so remember the homework is due Tuesday, so make sure you get started on that if you haven't already. Okay, it shouldn't take you too long. It's not the longest homework. Actually every homework in this class I think is relatively not that bad, but it's always good to start sooner rather than later. Okay. All right, so are there any questions I can answer before we get started? No? Okay. All right, so let's go ahead and get started. And so let's go ahead and pick up where we left off. Okay. All right, and so last time we were discussing this whole concept of equivalence, right? Equivalence with respect to equivalence with respect to how do we equate different amounts of money at different time periods, right? Okay, because what we talked about last time was that because of interest rates, and because of time, right, the value of money does not stay constant with time, right? So any money that you have now, you can always invest it to earn more money later. Okay, or you can spread that money out over a period of time using a uniform series. Okay, and so we've gone over 3 different forms of cash right now. Okay, so let me just review what those are and also kind of what they kind of visually look like in the cash flow diagram. Okay. Okay, and so the first form of cash flow that we went over was a present sum. Okay, and so present sum is a one lump sum of money that you have today. Okay, and so visually, if we kind of draw that out on a cash flow diagram, okay, it could be either a benefit or a cost that occurs on year 0. Okay. Okay. And so in here I have a cost that's taking place on the present day. Okay. And so this is a present sum of money because it's an amount that's happening, at a single point in time. Okay. All right, and so the next form of cash that we went over was a future sum. Okay. And so a future sum of money is just one lump sum of money that takes place sometime in the future. Okay. And so the future could be at any point in the future, right? And so basically a future sum takes place on could be at any of these times right here. Okay? As long as it's not 0, then it counts as a future sum. Okay. And a future sum, we gave the symbol F. And so just as an example, let's say that we have a future benefit on year 2. Okay. Right. And so we'll call this F right here. Okay. Okay. And so the reason I'm drawing these out as cash flow diagrams is that, later on today, we're going to discuss, what happens if you have a cash flow situation that doesn't really fit these kind of standard forms. Okay, so I call these kind of the standard forms of cash flow. And so you'll experience those a lot, in your, in practical situations. And so when you do have those kind of non-standard forms of cash flow, then you have to, convert them back to a standard form. Okay. Yes, yeah, a present sum can also be a benefit. It could be a benefit or a cost. Yeah, so the only thing with a present sum is that it occurs at year 0. Okay, so it could be either a cost at year 0 or a benefit at year 0. Yes, yeah, and so any benefit, a benefit is just any gain in money. So that would be an up arrow. Yeah. All right. And so, we went over a formula last time on how to convert in between these guys. Okay. And so that was our compound interest formula. And so to convert between a present sum and a future sum, we have this formula here. So we have F is equal to P, 1 plus I raised to the N. Okay. Right. And so if you have a present sum of money P, you can convert it into you can compute how much it would be worth at a future time if you know the interest rate and you also know the number of time periods. Okay.
But Professor,
Yeah.
I think the final equation is cut off from the screen.
Oh, is it?
I think so for me. I'm not sure about everyone else.
Well, it's. I'll write it again on the next page, just so everyone can see. Yeah.
Yeah, I don't think it's cut off. I can see it.
Oh, okay. I'll write it again one more time on the next page. But before we go there, are there any questions on this? Okay. All right, so let me just write out the equation just one more time, just so everyone can see. So F is equal to P, 1 plus I raised to the N. Okay. And so that's how you convert between a future and a present sum. Okay. Right. And so the third one that we went over, and so this is what we covered at the end of Tuesday's lecture, was a uniform series. Okay. And the symbol we gave for uniform series is an A. Okay. And so what a uniform series is this is mostly used to model your kind of recurring costs, either your maintenance costs or your salary costs. Okay. And these are basically a uniform payment that you make at regular intervals. Okay. Or it could be a uniform benefit that you get at regular intervals too. Okay. Okay. And so let me let me show you a uniform cost. Okay. Okay. Right, and so in this particular instance, we have a uniform cost or uniform series that takes place over 4 years. Okay. Okay. Right, and so it's 4 years because it goes through 1, 2, 3, 4. Okay. Right. And the key thing I want you guys to notice here is that there's nothing on year 0. okay? And so year zero is specifically reserved for just present sum. So basically every other cash flow, you won't have anything on year zero. And so any kind of cash flow that you have on year zero, that's going to be a present sum, okay? And so a uniform series always starts on year one. Okay. That's going to be important, okay? And so, we call this basically the standard form of the uniform series. And so it's going to it starts at year one, and then it goes all the way until the end, okay? Right, and so this is the standard form of the uniform series. Okay? So it starts at one and it goes to the end. Right? And so what we'll see on the kind of in the next section is what happens if you have a uniform series that doesn't go all the way to the end. Okay, then you need to basically convert this into a standard form. Right, but before I do that, let me go ahead and refresh your memory on the equations that we had. Okay. Because we also had some equations that converted between a uniform series and present sum and future sums. Okay. And so I'm only going to write one form of these equations because you can form the reciprocal one kind of pretty easily. Okay. And so let me give you the F and A formula. Okay. And so if you're going to convert between a future sum and a uniform series, you have F is equal to A. Okay. F is equal to A times quantity of 1 plus I raised to the n minus 1, all divided by I. Okay. Right, and so you can use that formula to convert between a future sum and a uniform series, and you can go both ways. Okay. Just make sure you plug in what you know, and then you basically do the other one. Okay. And so the analogous equation, or the other equation that converts between a present sum and a uniform series, is given by the following. Okay. And so we have A is equal to P times quantity I 1 plus I to the n divided by 1 plus I to the n minus 1. Okay. Right. And so that's the formula that you use to convert between a present sum and a uniform series. Okay. Right. And of course, there's two more equations that I gave you last time, but the way you got those equations is you just simply take this factor right here, which is the conversion factor, and you just kind of move it to the other side of the equation. Okay. And so if you have a situation where you're given, let's say that you're given a future sum and you want to compute the uniform series, you just kind of turn that guy over to the other side and you just solve for the unknown. Okay. Okay. Any questions on this? Okay. All right. And so those are the three cash flows that we've gone over so far, and I've given you kind of what they look like in a standard form. Now let's talk about what happens if you have a non-standard cash flow, and how do you deal with those situations? Okay. Okay. And so what happens if you have a cash flow diagram or a cash flow system that doesn't match any of the patterns that we've shown above? Okay. Okay. In these situations, if you have a pattern that doesn't match, the standard patterns, oftentimes what you're going to have to do is you're going to have to perform more than one conversion. Okay. And so usually you'll perform one conversion to transform it into a certain form. Okay. Whether that be, usually it's some kind of present sum. Usually present sum is usually the best to convert to, and then you're going to convert from that present sum to something else. Okay. All right. So let's do an example here to kind of show you what I mean. Okay? So to give you an example of both, what a non-standard situation looks like, and also what to do with it. Okay. All right, so in this example, let's say that we have a student that borrows $1,000 per year for 3 years. Okay. Right. And so, the student eventually has to pay this money back. But let's say the terms of the loan say that, they said that you can repay back the loan 2 years after the last year of the payments at a 15% interest rate. Okay. And so if we draw a cash flow diagram, it's going to look like this. Okay. Okay. So you have 0, 1, 2, 3, 4, 5. Okay. And so this student is going to be receiving $1,000 per year for the first 3 years. Okay. So let's draw that as benefits, a recurring benefit. Okay. And so let's say each of these are $1,000. Okay. And then 2 years after the money stops, so 2 years after year 3 is going to be year 5, then the student is going to pay all this money back. Okay. Okay. And so he's going to pay back in one lump sum in the future, F. Okay. And I forgot to give you the interest rate. And so let's say that the interest rate is 15%. And so it's, absurdly high. So someone is taking bad advantage of the student, unfortunately. Okay. All right. And so the question is, given this cash flow situation, let's compute, how much the student is going to pay back in year 5. Okay. So in other words, we're going to compute F. Okay. And so that's the goal of this problem. All right. Any questions on the problem setup here? Okay. All right. And so what we have here is, we obviously have a uniform series, right? And so we have a uniform series that's, $1,000 per year. Okay. And then we also have one lump future sum. Okay. And so the tempting thing to do that I think a lot of people try to do in this problem is that they try to use, this formula right here. Okay. Okay. This formula which converts between A and F. right? Which makes sense, right? We have a uniform series, which is going to given by our A. And then from there, we can compute F, right? So it seems pretty straightforward. Okay. The tricky thing here is that, you know, this F here occurs in year 5, right? Okay. Whereas the uniform series that we have here ends in year 3. Okay. Right? And so if we look back at the formula that we can use to convert this, right? We know that we have to plug in some value for n right there, right? And so the question is, you know, do we plug in 5 or do we plug in 3, right? And so the answer is both, actually, but you're going to do this in kind of more than one step, okay? And so you don't want to plug in 4, and so don't take the difference and plug that in because you're going to get the wrong answer, okay? And so in order to properly do this, you know, we need to convert, you know, we need to perform kind of more than one conversion, because what we have here is a uniform series that's not in standard form. Okay. Okay. And why is it non-standard? It's non-standard because it doesn't go all the way to the end of our cash flow diagram. Okay, so because it stops early, then this is a non-standard problem, right? And so we can't just take this uniform series here and then convert it into a future sum in year 5, because we're not really comparing apples to apples here, okay? Because the uniform series payment stops at the end of year 3, okay? And so we need to do this kind of in 2 steps, okay? And I'll show you what those 2 steps are on the next page. Right? So before we do that, does that kind of make sense about why we can't just do this? We can't just do a straight conversion between A and F?
Professor, I have a quick question.
Yeah.
If, let's say the future sum, if it did end on year 3, would we just easily use that one formula and just stick n equals 3?
Yep. Yeah, in those cases, if the future sum takes place at the same time that the uniform series ends, then you can just use just one formula to do it.
Right.
Yeah.
Okay. Thank you.
Yep. No, it's a good point to make. And so that would be another way that this would be a standard form problem, would be if the uniform series ended at the same time as when the future sum took place, right? But because they're different, then we have to do this in more than one step. Yeah.
Is the interest rate is happening through years 1 through 5, correct?
Yeah. So the interest rate is going to be constant throughout this entire process. Yeah, for most problems, there's only going to be one interest rate for the entire problem, and so I can't even think of a situation where it would change. And so, you know, usually when I give you an interest rate, it'll be constant through the problem, unless it's a problem where I ask you to solve for the interest rate. But that's a whole different class of problems that we'll go over later, called the rate of return. And so for now, you can always assume that the interest rate will be given to you, and then you know, it's something that you can just use throughout the whole problem. Yeah. Okay, and so let's go ahead and start solving this problem. And so, you know, we know that we have a a situation here where our uniform series is non-standard. Okay, and so let's go ahead and let's perform a conversion on this first in order to get it to a form where we can equate it with F. Okay. All right, and so there's lots of different ways that you can do this. Okay, and so there's you know, more than one way to kind of, you know, skin this cat, as they would say. But usually, you know, what I like to do and what makes the most sense to me is to convert any non-standard cash flows into a present sum. Okay. Because once you have a present sum representation of any kind of cash flow, then from there it's really easy to convert to anything else. Okay. And so if you can convert it back to a present sum, then that's usually a good thing. Okay. All right. And so let's take this uniform series here that takes place over 3 years, and let's convert it to a present sum. Okay. And so I'm going to use this formula here that I had on the previous page. And so let's say that we have A is equal to P times A is equal to P times I times 1 plus I to the N. Okay, divided by 1 plus I to the N minus 1. Okay. And so into this formula, we know what to plug in for most of these things. So we know that A is $1,000, right? Because that's how much we're getting paid on each period. I here is 0.15 for our 15% interest. And our N here is 3, because our uniform series takes place over three periods. Okay. All right. And so if we do that, I actually did something different in the notes, which is interesting. Okay. And so if we do that, let's go ahead and plug in all the values for this, right? So we have 1,000 is equal to P times, let's see. So we have, let me switch to standard calculator. Okay. Let's see. So we have 0.15 times 1.15 raised to the 3. Actually, let me use Google. That's a bit more reliable. 0.15 times 1.15 raised to the 3rd power. Okay. And then we're going to divide by 1.15 raised to the 3rd power minus 1. Okay. And so this is going to be 0.438. Okay. I'm just going to use 3 decimals here. Okay. And so this tells us that P is equal to, so we do 1,000 divided by 0.438. P is going to be equal to $2,283.11. Okay. And so now, after we perform this conversion, we have a situation that looks like this. Okay. Right. And so now we have a single lump sum at year 0. Okay. And we know that this lump sum is $2,283.11. Okay. And now we can compute F from here, okay? Right? And so now that we have a lump sum in the present and a lump sum in the future, we can just do a simple P to F conversion, okay? And so let's go ahead and use our P to F conversion. So we know that F is equal to P times 1 plus I raised to the N power, okay? Where this time, since we're going from time 0 to time 5, N is going to equal to 5. And then everything else stayed the same. All right, so let's go ahead and perform that math. Okay. And so we have 1.15 raised to the 5th power. Okay. And we're going to multiply this by 2283.11. And we end up with $4,592.15. Okay. Right. And so when you have a non-standard cash flow problem like this, you have to do it in multiple different steps. Okay. First, you have to get it to some kind of standard form, and then from that standard form, you can convert it to kind of anything else that you want to. Okay. And so in here, I used a present sum, because present sums are always really easy to work with. Okay. But actually, if you look at the notes, I actually did something a little bit different, a little bit more convoluted in the notes. And so, after this, why don't I show you what I did in the notes, just so that you can kind of see a different way that you can approach this problem, just so that you have kind of multiple different perspectives on how to do this. Okay. But does this make sense here? So, we had our non-standard cash flow. We first converted to a present sum, and then from that present sum, we could use that to convert to F, which is the objective of the problem. Okay. And so non-standard cash flows, remember that you probably almost always have to do more than one conversion.
Professor, just a quick question.
Yep. Mhm.
So it's non-standard because there was a time gap?
Yes.
Okay.
Yeah. Mhm. Yeah. And so when you're comparing a uniform series and a future sum, okay, then they both have to end on the same time in order for you to perform that conversion. Yeah. Mhm. Okay. All right, so let me show you the way that I did it in the notes, just so that you can see, kind of two ways to kind of skin this cat. Okay. All right. So let me draw the cash flow diagram for the problem one more time. Okay. And so we have, oops, a uniform series that occurs on the first 3 years, and then we have one future sum here on year 5. Okay. All right. And so another way that you can approach this problem is that you can actually convert this uniform series to a future sum. We can convert this straight to a future sum. Okay. And so we can just simply use the formula F is equal to A times 1 plus I raised to the n minus 1 divided by I. Okay. And so you can do this. And so you can use n is equal to 3, right? I is equal to 0.15. Okay. And then A is equal to 1,000. Right. And so if you plug that stuff in, then what you get is a future sum of $3,472. Okay. Okay. So you can do this, but this future sum here is not going to be at the right time. Okay. And so this future sum right here is actually going to take place in year 3. Okay. Okay. And so after you perform this conversion right here, you convert this uniform series to a future sum, right? That future sum is going to be placed on year 3. So if we draw our cash flow diagram one more time. Okay. And so now you're going to have just a single lump sum here of 3,472. Okay. But that's not the amount that we want. So the amount that we want takes place at year 5. Okay. But this actually does help us, because now we can take this 3,472 and then convert it to something 2 years in the future, right? So let me do this, right? So if we take our cash flow diagram and we kind of just separate it like this, and so we kind of throw out the first 0, years 1, 0, 1, 2, okay? And if I renumber this, okay? And so if we kind of consider a new cash flow diagram that starts at year 3, okay? Then what we can do is we can say that this 3,472 is basically a present sum, right? And if we consider this as a present sum, you can convert this into a future sum that's simply 2 years in the future. Okay. And so we can use our F and P formula that we had from before. Okay? And so instead of bringing that uniform series back to year 0 and then converting from there, we're taking that uniform series, converting it into a single sum on year 3, and then doing one more conversion to bring it forward onto year 5. Okay. All right. And so let's say that now we can say that F is equal to P, where P here is 3,472. Okay. We do 1 plus I. Okay. And then for N, we're going to plug in 2 because, year 5 here is just 2 years into the future. Okay. And if you plug all this in, you're going to get $4,590. Okay. Right. Which is essentially the same as what we got previously. Okay. So it's a little bit off. And so it's not exactly, we're off by like $2.15, but most of it is there. And when you're considering, $1,000, $2 is not going to make that big a difference. Yeah. And so this is just another different way that you can approach this problem, right? And so once again, you had a non-standard uniform series. And so we converted that into a single sum. But this time with this method, we converted to a single sum on year 3. And then from there, we just converted it 2 years into the future, to year 5. Okay. And so both work. And so, whichever way works for you, just go ahead and do it. But, the point I want to make here is that whenever you have a non-standard cash flow, try to convert it to a single lump sum first, whether it be sometime in the past or maybe sometime in the future. And then from there, you can kind of do whatever you want with it. Okay. Okay. So any questions on this? Okay. All right. And so that's non-standard cash flows. And so let's go over the last member of the cash flow family, which is the arithmetic gradient. Okay. And so this is the information that you need, or more like the formulas that you need to finish up the homework. Okay. All right. So arithmetic gradient, and so just this, and so it's arithmetic gradient is similar to a uniform series in that it's a recurring type of cash flow. Okay. And so it's much more closely related to the uniform series than the present sum or future sum. Okay. And in fact, you can kind of almost think of this as the flamboyant sibling of the uniform series. Okay. All right. And so what do we use this for? Right. And so arithmetic gradient is used to represent situations where your recurring payments are increasing over time. Okay. Okay. And so this is fairly common in engineering economics because probably anyone who's owned a car knows that as the car gets older, then the maintenance costs get higher and higher because more parts start to break, and so you have to pay more for them. Or maybe they just don't make the part for your car anymore, so you have to special order it from like Germany and it has to come here, and you have to pay for shipping and all that stuff, right? So it's very common for for older machines to have maintenance costs that increase with time. And so it's very natural for us to have a type of cash flow that kind of reflects this increase. Okay. Okay. And so let me draw it out for you first. Okay. Let me give you the standard form for the arithmetic gradient. Okay. Because the standard form looks a little bit strange, and I think it trips a lot of people up, right? And so let me kind of show you what I mean by that. If my freaking stylus would cooperate. So we have 0, 1, 2, 3, 4, 5, 6. Okay. All right. And so the standard form for the arithmetic gradient actually starts on year 2, believe it or not. Okay. And so it's a strange thing, right? Because a uniform series, I think, makes a lot of sense to people because it starts on year 1, right? Because that's when you start paying payments. Okay. But the arithmetic gradient will actually start in year 2. So actually 2 years after the kind of the present day. Okay. Okay. But after year 2, you're going to see that it goes up each year after that. Okay. Okay. Where the height of this arrow right here is given by G. Okay. This right here is 2G. This is 3G, 4G, and 5G. Okay. Right. And so, the question here is, how come it starts on year 2, right? So why doesn't it start on year 1 like uniform series, right? And so, it's a fair question. It's a good one. And so let me draw kind of a typical situation where, let's say that you've purchased a machine as part of an engineering company, and you know that the maintenance costs for these machines, they're going to start at a certain level on year 1, and then every year after that, it's going to go up. Okay. Okay. And so let's say that we have a, so let me write this as formally as an example. So let's say that this is an example of increasing maintenance costs. Okay. And so let's say that, maybe it's starting at maybe $1,000 in year 1. Okay. In year 2, it's going to go up to $1,200. Okay. Year 3, it's going to be $1,400. Okay. Year 4 is going to be $1,600. Okay. And so on and so forth, right? 1,800. And year 6, we have 2,000. Okay. Okay. So obviously, we have a situation here where, the costs are increasing with time. Okay. Right. And so, the question is, should we represent this, or how should we represent this in terms of our cash flow variables, right? And so we've just learned about arithmetic gradient. Okay. So obviously we know that's going to be a part of this. And the, but there's also something else that we can do here as well. Okay. Question. So if these are costs, how come the arrows don't point down? In the original diagram, I put the arrows pointing up just so that I would have room on the bottom. But arithmetic gradient could be either a cost that increases with time, which is what we have in this example, or it could be a benefit that increases with time, which is what I have in this top one too. So any cash flow that increases in value, we can use an arithmetic gradient to represent that. Yeah. Mm-hmm. Right. And so now the question is, do we represent the situation as a arithmetic gradient? And if so, what is the value of G? Okay. Right. Right. So because we can see here that we start at $1,000, right? And so, I think the tempting thing would be to set G is equal to 1,000 because that's what we started out with. But you can see that after year 1, we're only going up by 200 each year, right? And so the G, or the G value that you choose for this, is actually the amount that it increases per year. And so here the G value is actually going to be 200 because that's the amount that it's increasing year after year. Okay. Right. And so we have a G value of 200, and so that's good, right? Because we can see that the costs are increasing by $200 each year, okay? But then what about this 1,000, right? And in fact, every year after that, it's not just 200, it's actually 200 plus 1,000, right? And so to represent a situation like this, which is, you have a cost that starts on year 1, and then it increases every year after that, then you can represent this as a sum of both a uniform series and an arithmetic gradient. Okay, and so in addition to having a G of 200, we can also have an A of 1,000. Okay. And so let me kind of illustrate that for you. And so let's say that we have our G that's 200. Okay. And so if I draw a uniform series of 1,000, okay. Okay. And so all of these red arrows here represent, a uniform series of 1,000. And then every year after that, we're adding an increasing amount of 200 each year. Okay. And so the proper way to kind of represent the situation, which is, a maintenance cost that starts at a certain value at year 1, and then increases more and more again after that, is to first use a uniform series to represent what the cost is on year 1, okay? And then your arithmetic gradient is just however much more it's going to increase after that, okay? Year by year, okay? And so that's why in the standard form for the arithmetic gradient, we can see here that it starts on year 2, because we can say that's kind of the first year where increases are going to start to take effect, right? And so increases don't start on year 1, because that's year 1 is kind of where the baseline amount is going to be each year, right? And so it doesn't actually start increasing until year 2. Okay, and so it's a subtle point, but it's one that's really important for using arithmetic gradients, because it trips everybody up. It's I think the most confusing thing about this unit is what's the standard form of G, and how do we actually use that in cash flow situations. Okay. All right, any questions on this?
Professor.
Yep.
So why does G only happen around year 2? Can G not ever happen at year 1?
Yeah. So year 1, any cost on any basically any series that starts on year 1, we call that kind of the base amount, right? And so in this example here at the bottom, the base amount that we have here is 1,000, right? And so that cost actually doesn't start increasing until year 2. And so that's why for the arithmetic gradient, we started at year 2, and the standard form is for the arithmetic gradient to start on year 2. Yeah.
All right, thank you.
Yep. And so even though this gradient starts on year 2, it's important to make the distinction that n in this case, or the number of periods, is still 6, right? And so even though for the arithmetic gradient we have zero costs on or 0 cash flow on years 0 and 1, the number of periods for this is still 6. Okay. And so it's a tricky point, and I think it even though I'm kind of saying this here and putting a lot of emphasis, I think it won't really get nailed in until you actually start doing some problems with it. Okay. Okay, and so let me give you the formulas for converting between G and the other cash flows. Okay. Okay. All right. And so I'm not going to derive these. And so if you're interested in the derivations, they are in the notes, but just in the interest of time, I think we should just move on. Okay. All right. And so let's first get our formula for converting between F and G. Okay. Right. So we say that F is equal to G divided by I times 1 plus I raised to the n power minus 1 divided by I minus n, or is that times n? I can't even read my own notes. Minus n. Yes. Okay. Right. And so you can use that formula to convert between a future sum and a gradient. Okay. Next, let's get a formula that converts between P and G, okay? And so we have P is equal to G times. So this one's a little bit gnarly. So we have P is equal to G times 1 plus I to the n. Okay, minus I times n minus 1 divided by I squared times 1 plus I to the n. Okay. Right, so that's how you convert between P and G. Okay. And then finally, let's get a formula that converts between A and G. Okay. And so we have A is equal to G times 1 plus I to the n minus I times n minus 1 divided by I 1 plus I to the n minus I. So, all these formulas are pretty gnarly, but remember, I don't expect you to memorize these formulas. All I want you guys to do is to use them in the right situations. Okay. And so keep your notes handy whenever you're doing your homeworks, just so that you can pull up the equations whenever you need to. Okay. The important thing for these formulas to remember is, which cash flow forms are you converting between, right? And so remember, these formulas are always used to convert between one form to another. And so as long as you know which form that you're using and which one you're converting to, then you can pick out the right formula that you had to use. Yeah. I don't memorize these formulas. These are pretty gnarly, right? And these formulas don't even make sense. And so if you think about like fluid mechanics formula or like a structural mechanics formula, at least those you can kind of make sense of why certain terms are there or not. But these are just just random kind of stuff. I mean, they're not random. I mean, they have a derivation. And, I'm not an economics person, so it doesn't make as much sense to me. But if I were to try to memorize these formulas, it would be just pure memorization without any kind of conceptual understanding. And that's always really hard to do. Yeah. Yes. So these are all gradient conversion equations, so they all have G in them in some way. Yeah. Okay, and so let's do. I want to do one quick example to kind of show you how to use these formulas, and then we have one more topic I want to cover today. But before I jump into that example, are there any questions on this? Okay. All right, so let's do an example to kind of show this in action. Okay. All right, and so in this example, let's say that you have a friend that just purchased a new car. Okay, and then for this car, he knows that the maintenance costs for this car are going to go up every single year. Okay. And so, you've talked to the dealer, right? And so the dealer basically gave you this schedule for the maintenance costs. Okay, so he gave it to you in a table. Okay, and so in year one, it's going to cost $120 for maintenance. Okay. Year two is going to cost $150. Okay. Year three is going to be $280. Year four is going to be $210, and then year five is going to be $240. Okay. All right. And so your friend, he sees this maintenance schedule, and he says that, I don't want to have to worry about this every single year. And so what he wants to do is he wants to set aside a lump sum of money right now that's going to cover the costs, all the maintenance costs for 5 years. Okay. Okay. And so let's say that your friend is setting aside money in a bank account with 5% interest. Okay. Okay. And so the question is, how much money should your friend set aside now, put into that bank account to cover all of this, cover all of these costs? Right, emphasis on the now. Okay. All right. And so since we're solving for an amount of money that we're putting aside now, we're going to be solving for P, right? Okay. Right. And so basically we're going to take that schedule up there and then convert it all into a P. Okay. All right. So any questions on the setup for the problem? Okay. All right. And so we have the schedule here. Okay. We see that it's going to start to cost, or the first year's cost is going to be $120. And then every year after that, it's going to increase by 30. Okay. And so going off the same kind of situation that we covered here, right? What we can say is that this maintenance cost schedule can be broken up into a uniform series and an arithmetic gradient. Okay. And so we're going to have both a value of A and a value of G for this problem. Okay. And then once we've determined what A and G are for this maintenance schedule, then we can easily convert them to P using our formulas. Okay. All right. So what should I put for A in this case? So what should I put for the uniform series amount?
The year one value.
Year one value, yes. And so in this case, it's going to be 120, okay, because that's what the maintenance cost starts at. Okay. And then what should G be in this case?
30.
30, yep. You got it. Yep. And so now we have an A value of 120 and a G value of 30, okay? And then now we can just simply use our formulas that convert between P and A and then P and G, and then plug in for A and G to convert P's. Okay. Okay. And so our two formulas for that. Let me do the P and A formula first. Okay. So you have P is equal to A times 1 plus I to the n minus 1 divided by I times 1 plus I to the n, okay? Right? And so if we plug in A is equal to 120, okay, we know that n here is equal to 5 because we're doing these costs for 5 years. And then I here is 0.05, right? And so if we plug all those things in, we can see that our P value here is $520. Okay. Right. And so that's the first value of P that we have. Okay. And so that takes care of the A value. Okay. And then next we need to convert this G of 30 into P. Okay. Then we can add them together with this, and then that gives us our total P, for this entire problem. Okay. Okay. So any questions on this so far? Okay. All right, so let's convert this G into a P too, okay? And so I'm going to use one of the formulas on just the previous page, okay? The previous page of the previous page, okay? Right? And so this is going to relate P and G, right? As we said, P is equal to G times 1 plus I raised to the n minus I n minus 1 divided by I squared times 1 plus I to the n, okay? We plug in G is equal to 30, N is equal to 5, I is equal to 0.05. Okay. What we get is this P is equal to, $247. All right, and so to get the total amount that we have to put aside now, we can just add together the P from the previous page and this one, okay? And so from the previous page, we got a P of 520. And so here we have a P of 247, okay? And so we add this together. And we get a total P value of $767, okay? And so if your friend takes, $767 right now and puts it into a bank account with a 5% interest rate, that's going to cover all of his maintenance costs over the 5 years. Okay. All right. Any questions on this on the end of this example here?
I have a question.
Sure. Mm-hmm.
Looking at the third gradient formula, that A equals to G, why didn't we start with that one? Because that's where I thought you were going to say, but then you ended up converting those to P first and then using the P equals to G formula.
Yeah, so actually, we did two different calculations here. So we had one contribution from the arithmetic or the uniform series A, and then one contribution from the G. And so the G is how much it's increasing, right? And so, in this problem, we wanted to convert everything to a P in the end, right? And so what I did here was I kind of did two different calculations, right? And so if you kind of draw the cash flow diagram for this. Okay. So the cash flow diagram looks something like this, right? And so here we start at 120. And then every year after that, we go up by $30, right? Okay. And so what I did was I said that, this is, this situation we can kind of split into two different cash flow diagrams that we can kind of, consider separately, right? And so I split this into one cash flow diagram that looks like a uniform series, okay? Where this uniform series amount was 120, okay? And then the other one that I split it into was the gradient. And I kind of considered both of them separately, okay? And so what I did was I took this first cash flow diagram here. I converted this one to a P, okay? And so now this is just one single P at the beginning, okay? Then I took this cash flow diagram, and then I converted this one to a P, which is a single P at year 0 right there, okay? Okay. Then what I did at the end was I kind of just added them both together because that's going to be the total amount of money that you need to save up at the present day. Yeah. Yeah. So this wasn't a non-standard problem, and so this isn't one where we had to do kind of multiple different sequential conversions. Here I kind of split the problem into two and considered both parts kind of individually, and then I kind of added them together again at the end in order to get one final answer. Does that make it a bit more sense?
Yes, thanks.
Great. All right, any other questions on this example here? Okay. All right, so the last thing I want to go over today is a very useful tool, probably a tool that you're going to use a lot in this class, okay? And that's the compound interest tables. Okay. All right. And so in this class, what we're going to be doing a lot of is, we're going to be doing conversions, a lot of conversions like we have been doing today, right? So you have cash flow in one form and you need to convert it to another form, right? And so these conversions are going to be kind of fundamental to the economics portion of this class. Okay. Cash flow conversions are really important, but using the formulas can be really cumbersome, right? And that you can even say that they're really annoying. Right? Okay. And so what if I told you that there's a way to perform these conversions without having to use a formula? Okay. Because someone figured this out back then, that using all these formulas, especially for big complicated problems, can get really annoying, right? And it's not even kind of a like an exciting calculation to do. It's like just punching in numbers into this really long, big, complicated formula, and then all for what? It's just for converting one cash flow to another. And so someone figured out that this is, people would get really upset doing this a lot. And so what they did was they basically took those formulas and then created a big table for them. Okay. Okay. So let me give you an example of how these tables are, or what's in the tables, how to read them, and then how to actually use them in your calculation. Okay. All right. And so let's do kind of a simple case, or actually maybe let's not do a simple case, so it's actually useful. Let's do a P and A conversion. Okay. And so from the previous example, we know that we have the formula P is equal to A times 1 plus I to the n, okay, minus 1, all divided by I times 1 plus I to the n, okay? Right. And so this isn't even the worst one, but because it's not one of the gradient ones, but it's still pretty annoying to do. Okay. Let me take this formula and let me divide both sides by A. Okay. And so on the left-hand side, we're gonna have P over A, okay, is equal to 1 plus I to the n minus 1 divided by I, 1 plus I to the n. Okay. And so let's look at the expression that's on the right-hand side. Okay. Okay. And so if we look at this expression, it's kind of a gnarly expression, but we can see that the only variables that are there are I, which is the interest rate, n, which is the number of periods, and also 1, but 1 is just 1, right? So one is just one guy, right? And so really this only just depends on I and n, right? So it's kind of a complicated expression, But if you know I and n, then it'll give you the right values. Okay. And so if you look at all the formulas that we've actually been using throughout this entire last few class sessions, they all actually share the same characteristic, right? And so what you can do is you can kind of move all the cash flow items to one side of the equation. And on the other side, you're left with something that just depends on the interest rate and the number of periods, okay? And so this is really nice because what you can do is that, if you're given the interest rate and the number of periods, instead of actually plugging into this formula here, what you can do is actually, you can just say that, what is this conversion factor right here? And then if you can just look that up into a table, that would be really convenient, okay? And in fact, that's exactly what the compound interest tables are. And so let me give you a drawing of what they look like on the next page, and then we'll kind of redo a calculation that we did before with the compound interest tables, and we'll see that it's a lot easier than actually plugging the formulas. Okay. All right. Any questions on this? Okay. All right, and so the compound interest tables is a PDF, and so I'm going to post it on Canvas in a second, okay, right after this class, and it looks like the following, right? And so in one column, you're going to have the number of time periods, okay, and so that's going to be n, and so this can go 1, 2, 3, 4, okay, and then from here, you're going to have a bunch of different conversion factors, okay. Okay, so basically every combination of our cash flow types in the numerator denominator are going to be listed in this table. Okay. And I'm running out of room. Okay. But you kind of get the point, right? So every different combination of the different cash flow types in the numerator denominator are going to be here. And then listed in this table are going to be a bunch of decimals or conversion factors, right? So it might be 0.1, 0.2. I'm just listing out just kind of random decimals for now. Okay. Okay. And there's kind of more throughout the table. Okay. All right. And so the way you use this table is you need to ask yourself, what am I converting to and what am I converting from? Okay. Right. And so the cash flow type that you're converting to, that should be in the numerator of your expression, okay? And the cash flow type that you're converting from, it should be in the denominator, okay? And so if we do kind of the previous example, okay? And so in the previous example, we converted from a uniform series to a presence sum. And so this tells us that what we need is a P over A conversion factor. Okay. Okay. And so if we know that we need a P over A conversion factor, we're going to look at this column of the table at the row that we want. Okay. And so let's say that, let's say that n is equal to 5. We're going to look up n is equal to 5. We're going to look over the P over A column, and that's going to give us the conversion factor that we need. Okay. All right. And so the way that you kind of write this down is you say that P is equal to A times the conversion factor of P over A with a interest rate of, let's say, 5% over 5 years, okay? And then this conversion factor is what you can look up in the table. Okay. Right, so I'll go over this again at the beginning of next class, just because we're just about out of time. But let me kind of finish this example for you, just so that you know what to do. Okay. And so if I look up on the compound interest tables, I look at the interest tables for 5%, and I look for n is equal to 5, and I look for the P over A factor. I can see that this factor right here is 4.329. Okay. And so if we finish up this calculation, we could say that P is equal to 4.329 times A. Okay. And if we plug that into the calculator, and so let's say that we're redoing the last example, and so our A is equal to 120. Okay, and so we multiply that by 4.329, and we get $519.48. Okay, and so very, very close to what we got with the formulas, but we did it without having to plug into something really, really cumbersome. Okay. All right, so I know we're out of time, and so I won't hold you guys any longer. And so we'll go over this again on Tuesday, just because I know this was a little bit rushed. But the compound interest tables is a very, very useful tool for you to use, throughout this class. And in fact, actually, I expect most of you guys to use the compound interest table versus the formulas. Okay. All right, so thank you guys for tuning in today. I apologize for keeping you for a couple more minutes. So enjoy your great long weekend. Remember, Monday's a holiday. Okay, and I'll see you guys on Tuesday.
Professor,
Hey, yep.
quick question.
Sure.
For using the tables,
Yep.
If we don't have the book, are you gonna post? Like, are they already posted, or are you gonna post?
I'm gonna post it. I'm gonna post it right now, and so it'll be you'll be able to download it from the homepage on the course website in like 10 minutes.
Okay, perfect. Thank you.
Yeah.
All right, you have a good weekend.
Thanks. You too.
Professor, I have a quick question.
Sure. What's up?
So I had a little power outage and I probably missed like 10 minutes of class or so where you're going over the arithmetic gradient. Do you mind just going over it really quick? Just one
Oh
more
yeah,
time?
yeah. Let me see.
Yeah, sorry about that.
Oh, no problem. Let's see. Arithmetic gradients. This guy. Okay. All right. So the idea with the arithmetic gradient is that it's a cash flow that increases with time, and so it's kind of the close cousin of the uniform series, and so it's a recurring cash flow, but it's you can see here that it increases with time. Okay. So you use these you use the arithmetic gradient for situations where like either you're going to have a maintenance cost that increases over time. Or maybe you expect your benefits to increase with time as well. Okay, and so the key thing with the arithmetic gradient is that it always starts on year 2. Okay, because if you have a situation, like we have on the bottom here, or kind of like the example that we did, where you have a recurring cost that starts, that has like a base value at year 1, and then increases after that. Okay, what you can do is you can split up that thing into a uniform series and an arithmetic gradient that goes on top of that. Okay, and so the arithmetic gradient, the thing to remember for that is it's purely just the amount that it's increasing year to year, right? And so in this example on the bottom here, you can see that the cash flows are increasing by 200 per year. Okay, and so the G here is going to be 200. Okay, and then this is going to be added on top of a uniform series, which is 1,000, which is what it is on year 1.
Is that it?
Yeah, and then and so you were here for this example, right? For the maintenance cost for a car.
Oh, I actually wasn't. I was trying to write as quick as I can.
Oh, okay.
I didn't even
Okay.
get the formulas down.
I see. Yeah. So this example here, was kind of an example of how do you take an arithmetic gradient and convert it back to a present sum, right? And so in this problem, what I said was that your friend just purchased a car, and then the maintenance costs for this car are going to go up with time, right? And so it starts on at 120 in year 1, and then it's going to go up by 30 each year after that for the first 5 years. Okay. And so what I did was I said that this kind of payment schedule here, we can kind of break it up into two contributions, right? And so one contribution would be the uniform series, and so the uniform series would start at 120 because that's how much the that's how much the costs start at year 1. Okay. And so first thing is we have an A of 120 here, and then this amount is increasing by 30 each year after that, and so we have a G of 30. And so we need to take both of this A is equal to 120 and this G is equal to 30, and then convert those into P's using the formulas, using the cash flow conversion formulas.
Okay, and then your A, it's always gonna be year 1.
Yes, yeah. So in this case, this example kind of mirrors this situation right here, where you have a kind of a cost that increases with time, but it starts at a base amount at year 1. And so the A is going to be your base amount at year 1, and then your G is going to be just however much it's increasing on top of that.
Okay.
Yeah.
Professor, I just have
Yeah.
a quick question.
Mhm.
Do you usually upload the videos the same day as lecture?
So I try, but I'm also like a little bit lazy because I
Oh,
start the upload and I kind of forget about it.
right.
And so they're usually on YouTube the same day of, if not later in the evening. But usually sometimes I forget to post it on Canvas until the next day.
Okay, thank you.
Yeah. Mhm.
All right, thank you, Professor.
Yeah, no problem.